Okay, so good evening. In today's recitation, I'll walk you through some of the details of the core map, which is basically where you should try and start for assignment 3. So we'll talk about initializing the core map, what it is, what it's used for, and we'll also slightly delve into page tables and how they're supposed to look. So to start off, the core map data structure is an array of core map entries. And this design paradigm you've already seen before, because this is what you use for your file table. Your file table had entries. Your process table also had entries. So in that way, the core map is very similar to that. Again, this is a global structure that's used for the whole system, so it does need synchronization. Every process accesses the core map, and each entry in the core map is supposed to represent a page of physical memory. Now, this is an important note because as you get into assignment 3, we're going to be talking a lot about physical memory and virtual memory, right? So the core map represents a page of physical memory. And because there is an entry for every page, overhead becomes critical. Your entry size cannot be large, because if your core map entry becomes large in size, then adding extra memory is not going to help you at all. Like, for example, if you assume that 10%, right, 10% of memory of a page size is being used up for a core map entry. What does that mean? So you have 4K as the page size, 10% is like 40K, or 400K in fact, sorry, 400 bytes. So that is the size of a core map entry, right? And now adding extra RAM is not going to help, because every 10% of that is going to be used up even for that extra piece of RAM, right? So overhead is very critical. You want to make each entry as small as possible. And so where the core map fits into the whole OS 161 code is that once you implement the core map, you have to also implement these two functions, alloc k pages and free k pages, which is going to link it to kmalloc, right? And once you have those functions implemented, you should be able to run some of the code and see how your core map is performing. And there is a small trick here, right? So how do you allocate space for core map? Until now, the process table was kind of static. The file table was being kmalloc. But to kmalloc, you need the core map. And to have a core map, you potentially need kmalloc. So we look at how to solve that problem as well. The hint is there are two functions called ram getSize and ram stealmem, which help you to solve that problem. All right, so let's look at the data structure itself. So each entry in the core map is supposed to have a pointer to a page struct, right? That contains like the page specific information, like where does this page start? What is the physical address of this page? Where does it end? We know that, it's 4K, so we know where it ends. But each page also needs to have a lock associated with it, because remember, now memory is being maintained in terms of pages. So if another process is accessing this page, you don't want some other process to kind of swap it out. Okay, so that's the page struct. And then there's the CPU index. That is basically used for the TLB. It's kind of mixed with the next field, which is the TLB index. So each CPU has its own TLB, and the CPU index tells you which CPU this page is on, which CPU's TLB this page is on, right? So we use the CPU index and the TLB index together to kind of either evict it from the TLB or figure out which TLB you have to reset, right? And then we have a few booleans that basically tells us whether this page is being allocated as part of kernel. Is it a kernel page? Is it the last page? We'll come back to this. This is slightly important. It's useful for optimizations. And has this page been allocated, right? Because the core map, once it's initialized, has an entry for every page. Now, that does not necessarily mean that each one of these pages has already been allocated. It's available for use, right? So as pages are being allocated, we're going to mark them as allocated, so that when we are trying to allocate a new page, we can skip over those that have already been allocated. And is it pinned? Now, pinned is also a slightly tricky concept. Basically, if the page is in use, then you pin it. If it's not in use, then it's a potential source for eviction, right? That page can potentially be evicted. Now, if this is your core map entry, and you want to figure out the size of this, we see that the size is 28. How do we compute that? Well, the first one is a pointer. Pointer is size 4. And all the others are basically integers, right? I'm pretty sure that bool also goes back to an integer. So you have 1, 2, 3, 4, 5, 6. So 4 times 6 is 24, plus the address is 28. This is the size of a core map entry. And how does this compare? Well, for every 4K, you spend 28 bytes for just this metadata, right? And that works out to like 0.7%, which is not that bad. But of course, here we are excluding the size of page struct. Just having a pointer is useless if there's nothing at the end of it, right? So we are excluding that, and excluding that, we have 28. Now the trick is, can we do better than this? 0.7 is not that bad, but can we get even lower? And we can, in fact, by using this concept called bit fields, right? So in C, basically the trick is that the booleans, right, you don't need 4 bytes for them. They're just true or false. You can represent that with just a single bit. And that's what we're going to hook into and save some more additional space. And the way to do that in C is to give a colon and give the size. So for example, when I say CPU index :4, that means I'm allocating 4 bits for it. And so with 4 bits, you can count, it's unsigned, so you can count up to 16, 0 to 15, right? We don't have that many CPUs, but just, you can use any number you want. It's kind of arbitrary. TLB index of 7 is important because you have 64 entries in the TLB, which is 2 power 6. The 7 is basically used for, because it's an int, you want sign there. You want -1 to represent like invalid entry or something, right? Is_current page is 1 because all of those are 1 because they're all Boolean, right? So if you do it this way, you see that the size of the code map entry is just 8. Now how is it 8? Because the address is still 4. All the others account for 7 plus 4, 11, 12, 13, 14, 15 bits. That's all. And that can fit inside a single integer, so it uses 4 bytes for it. The remaining bits are still unused, so you have a total size of 8. Okay, so again, as I mentioned, code map and kmalloc fit in through the interface of alloc k pages and free k pages, right? So what does alloc k pages have to do? First, you check whether you're allocating multiple pages or a single page. You have separate functions for each of these, right? Pseudocode, this is how it would look. If the number of pages is more than 1, then you call this function that's supposed to allocate multiple pages. If it is just 1, then you allocate a single page. And then you use that macro to return the address, right? So what is the difference between these two functions? In a multi-page allocation, all you have to do is find consecutive pages. And once you find the consecutive pages, you just give the start address of those, of the contiguous region, right? But the problem is you may not always have consecutive or continuous free pages to allocate, in which case you'll have to sometimes evict, right? And here you're free to, I think you're free to implement your own eviction algorithm. I don't think it matters. The simplest would be to do something like random if you just want a quick working solution. All right, so for a single page allocation, all you have to do is find a free page, mark it as is allocated, and then if it has been asked to be pinned, then you pin it. Usually all kernel pages are pinned, right, because you don't want those to go out. Okay, so we spoke about this page struct, which I mentioned there. So what does that have to contain? So the page struct is supposed to represent a page itself, right? And this is like the logical page. So what does it have? It has a physical address, which is the start address of that page. It's supposed to have a swap address in case it's swapped to disk, and it's supposed to have a lock so that nobody else can modify this page while it's being used by a process. Okay, so what is the size of this? If you were to add this, this would be another 8 plus 4, 12 plus the size of spinlock, right? Not that bad. Moving on. So allocation of the core map has to happen very early, right? And the reason is, if you look at, let me just pull up the boot process. So all right, so if you look at the function k main, or sorry, boot kmain calls boot, there is RAM bootstrap that happens very early, right? And RAM bootstrap doesn't really do much except get the size of available memory. So this makes a call to main bus, which I think hooks onto sys161 itself and then gets the size of RAM. Now, the bootstrap for the core map, or where you initialize core map, has to happen sometime in between the RAM bootstrap and thread bootstrap. Why? Because thread bootstrap will call thread create, which in turn calls kmalloc. So you need core map to already be in place so you can handle that kmalloc call, right? So it has to happen roughly somewhere here in this gap, and what it has to do is find the size of available memory, look at the function RAM bootstrap. That will give you an idea as to how it's done, right? Once you get the size of available memory, you have to allocate some of it for the core map itself. The core map is being used to manage the remaining portion of memory, but the core map doesn't manage the memory it's occupying itself. It cannot, because otherwise you're corrupting the map itself, right? So some space goes for the map, and the map is used to manage the rest. So how do we get space for the core map? That's where this function RAM steal mem comes into play. So what RAM steal mem does, or let me first talk about RAM get size. So what get size does is it tells you the starting address of memory and the end address of memory, right? And what steal mem does is, depending on how much you ask of it, it will move the start address by that much. So the next call to RAM get size will actually return the new start address and the same end address, right? But there are some problems with this. Ideally, you should not call steal mem after a call to get size. Now, this is not a hard constraint. This is not in any way a hard constraint, but the problem is, if you call steal mem after a call to get size, what happens is the initial values that you got from the call to get size are now sort of invalid, because you stole some memory, but because get size said you have all the way from 0x0 to whatever else, you may be modifying the memory you just stole, right? So ideally, you don't want to do that. In which case, to allocate core map, what you have to do is call get size. It's just a warning, right? You have to keep in mind that calling steal mem after get size could potentially put you in a place where you're corrupting the memory you just stole. So you just have to keep that in mind. It's not a hard constraint that you should not do it. So the trick here is to first call get size. So you get like 0x0 to something else, and then that gives you the total size of memory. And because you know the page size, you can calculate the number of pages, right? If you have the number of pages, let's say there are 300 pages. Once you have the number of pages, you know how many entries need to be there, 300 entries. And we also know the size of each entry. We calculate it to be 8 bytes, right? So now we know exactly how much memory we have to steal. So this can be done either by calling RAM steal mem, or this can be done by hand. You can look at what RAM steal mem does, and you can reproduce the same logic without ever calling RAM steal mem, right? But the point is that, remember, core map is only used to maintain the memory beyond the space that it's occupying. So wherever, let's say core map stole like 1200 bytes. So round that off to like page size. That's the start address. It goes all the way up to the end. That was returned by get size. Okay. So we then move on to the process address space. Now, if you look at address space.h, you will see that the address space has all these entries, but they're not really being used. They're set to 0, I believe, and then that's just it. That's all the dumb VM does. But all this is happening because I believe dumb VM actually manipulates physical pages itself. There is no virtual layer in between, so there is no need to manipulate any of these, right? But all that is going to go away because the whole assignment is about implementing virtual memory and this layer of abstraction. So how do we do that? We first create like a wrapper around page struct. Remember, the page struct is used to reference a logical page, right? And the wrapper is basically to reference a bunch of logical pages or a collection of logical pages. And so we first write a small function like this. It just is an array of pages. And what we do is we add this to the address space, right? And we add it to the address space in such a way that now the address space is an array of these wrappers. So it's an array of collection of pages. It's a two-dimensional array, basically, right? And once we do this, we'll look at some of the address space functions and what the logic should be for implementing them. And at that point, it will become clear as to why you want such a wrapper. Okay, so, but then what about the heap? Because we have to allocate stuff on the heap as well, right? The heap will again become one of these objects. And the heap is managed by a call to sbreak. We'll handle this call later, so I won't go into too much detail about the heap, but the trick is that the heap itself is a collection of pages, just like how I mentioned. And calls to sbreak just has to, in the worst case, calls to sbreak has to manipulate this array of pages, right, or collection of pages. So what do we have in the address space structure now? We need to have that array of objects. We need to have the index of the heap. So the heap, the index is basically the index into that two-dimensional array, right? One of those indices points to an array of pages that is being used as the heap. That's what that means. Yes?
Does the two-dimensional array contain everything from 0 to SSFF?
No, not necessarily. This happens on demand, right? So when there is a page that is being requested, a physical page is allocated, and then a corresponding virtual address is filled in. And basically what you get is an L page, a logical page, or page struct as I called it, right? And that's what goes in there. Okay, so potentially this is sufficient for the address space, but let's kind of verify that based on the functions we have to implement. So we have ASST create. That's one of the first things, right? So what do we have to do here? We just have to allocate memory for the array itself and just set default values for the other fields. By the other fields, I mean like the heap object is break and the max break, right? Because the address space has been created, it's not being used. All right, so for ASST copy, what do we have to do? The basic idea of laying it out in this way, dividing it into page struct and then this array, this wrapper class around page struct, is that it simplifies ASST copy. So all ASST copy has to do is say, for each entry in that array, do a copy, right? And then you, of course, you have to implement that functionality, but what is each entry in that array? It's of type page struct. So copy the page struct. But how do you copy a page struct? Because a page struct is basically a reference to a page, right? But if we go back to how the page struct looked, it has a physical address. And we know the page size, 4K. So when we are copying a page struct, all we have to do is create a new page, get a page from the code map, right? Copy stuff starting from that address up to 4K length. And then we have made a copy of a page, right? Add that new reference into the, so in ASST copy you have this new address space, right, that you're creating. So add that reference into the array of objects there, and that should be all. Just do this for every entry in that two-dimensional array, right, and you should be done. ASST destroy, similar thing, just go around the array destroying each one, mark those pages in the code map as free, as in is allocated as false. ASST activate is basically called when there is a context switch, or I think also an exec. Yes. So what does that have to do? It's just saying that there is a new process that's now executing, so I need to invalidate the TLB, right? Because I can't be using the old process's TLB with the new one, because there may be some virtual addresses that are mapped to different physical addresses. So I just clear out the TLB on the particular CPU in question. The current CPU there is a macro that always points to the current CPU, which is cur CPU, just like cur thread. So you can use that to reference the CPU. And you just need to clear the TLB on it. So what about ASST defined region? This is called a few times in load elf. I also, while you're implementing your sbreak, you will also have to make calls to this function. So this is potentially one of the more tricky ones. So what you have to do here is ASST defined region actually takes in a virtual address as one of its arguments. So first thing you do is align it with the page size, and then make sure there are no overlaps, right? Because if the region that you're defining now has an overlap with one of the regions you've already defined, then you're starting to corrupt your own memory. So make sure there are no overlaps, and then just add it to the array. Now we move on to some of the more complicated address space functions. AS prepare load, return 0. AS complete load, return 0. And then there's define stack. Define stack is a little tricky. Again, this goes back to sbreak system call. We'll come back to this when we get to handling the heap as such. Any questions?
Address space should be, when you say address space, is it the whole of 4 GB or is it?
So well, I think dumb VM has a limit on it.
508.
No, I think it's smaller than that. I think it's much smaller than that. Right? Okay, so yes, when we say the address space, we mean the whole thing, but you don't have to manage each one of them. You don't have to allocate all of it, because remember, so even when the user program calls malloc, right, a page needs to be allocated. But the trick is that you don't really have to do any of that work. You can do like lazy initialization on it. You can just push off all that work until he actually reads or writes from it. And that's when you actually need to make sure there is a page corresponding to that virtual address. So when there is a fault, you go and check whether that's a valid entry, and if it is, then you create a page and then the fault is handled, right? You just load that into the TLB and it works fine.
And the two-dimensional array of pages is a list of all the allocations with contiguous pages each time you allocate.
A list of all?
All allocations which we made to the process.
Yes, and the list of pages in that allocation. Yes.
So if we made one allocation lot of times, there will be like in second dimension.
Yeah, the second dimension will be only one. But that's fine, because this is how you handle like either single page allocation or multiple page.
So how do we allocate that array, two-dimensional array? I mean, what space do we give it when we allocate it?
It can be a list, right? It can be like a linked list, in which case you do it on demand. So you have to add a new entry, go ahead and add one. Right? So yes, I get what you're saying. So you can't really allocate the first dimension because you don't know how many definite AS-defined regions are going to be called. Yes, that's completely valid, in which case you just make it like a linked list. So add entries as you go along. And while you're iterating, you just check for null, because that's the terminating condition, and then you've iterated over the whole set of objects. What does it do? There are some comments on top of the function. I am not sure what it is used for. Jingao, do you know what it's used for? AS prepare load and complete load. What is it used for?
So there is some regions that may be redundant, for example, in the code region. So when we define region, we prepare the definition of the region, right? Before you, so prepare load told you that I'm going to write some content to the redundant region. You better change the definition of it so that I can write that table.
But we don't really need to implement it, right?
We do. Why not? So if we, so on a fault, if you receive a fault, the user tries to write your redundant page.
Right.
But in certain cases, you shouldn't refuse that. That's what prepare law does. So prepare law told you that I'm going to write some content that is redundant region. So you better set the permission to be writable for that.
I see, but
E not L.
I don't think I had to implement this to get marks. No, but there are no arguments passed to it. So how do you say it's read or write?
No, well, you can't really know which region are read on which region.
Right, but I never had to implement it. Well, it's not complicated, but I thought we have to have a look at S-break first to understand how we move the top.
No, you just said directly to the top.
Right, but we still have to understand what S-break does and how it functions. So I thought it's best to handle that when we get to S-break. So the short version of what S-break does is it just asks you to move the stack boundary, right? So when you're trying to allocate more memory, you move. Oh, sorry, heap. Sorry, I don't mean stack. Sorry, my mistake. So you just move the heap boundary, and it keeps moving down. But then there also needs to be this this guard band between the heap and stack, because remember the stack grows downwards and the heap grows upwards, but they can't overlap. So S-break is responsible for managing the limit. You just keep pushing it, and as you push it, you also call AS-defined region, because you just allocated this new memory, right? So you call AS-defined region and do what it does for that new space that you've allocated. No, I think we've just done it very differently. Okay, so this is kind of all I have. I hope I've not missed anything, because we had a conversation, me and Jinghao, about what to handle each week in recitation. And I think I'm just leaving a lot for him to handle, because I'm not very good with recitations myself. But yeah, I'll be around to answer any questions. I think he'll also be here. So if you guys have any questions, go ahead and feel free to ask.